everybody. It's a pleasure to compliment Chair of Excellence, Professor Chenchang Zhu from the University of Göttingen. Chenchang has made significant contributions to different geometry and quantum geometry, spanning from study of higher structures, groupoids, differentials, structures. So she is a very famous mathematician, and she started by getting the gold medal at the Olympics, correct? not for high jump. And then she also won the Lucy Award from Technical University and the Lift-Off Fellowship from the Clay Institute, among other achievements. So it's my great pleasure to introduce her, and she's going to speak about higher structures in symplectic geometry.
Thank you very much. Thanks for the introduction. Well, I try to be entertained about higher structures in symplectic geometry. So the story today starts, let's say, 400 years ago, like crossing this Mediterranean. So here we have a gentleman using the telescope that the Spanish captains looked into the vast sea and ocean, put into another endless object, namely the sky. And he found that there are 4 moons. Among other astonished things, he found there are 4 moons turning not around the Earth, but around Jupiter. At that time, it was breaking news to human confidence, right? Like ego. As much as artificial intelligence breaks our confidence today, we are not unique. Not everything turns around us, and our intelligence is also not unique. Well, this very clever gentleman, after 30 years, he also observed like a little ball jumping from point A to point B. He found out that it's not the fastest descent curve is not the straight line. Well, it was observed also by the other gentleman 2,000 years ago. But even though I'm Chinese, I'm sure he didn't have any math formulas. Like the one who has math formula is Galileo, right? So he has some math formula, and he tried to describe this mathematically. He tried to argue, but he found out that he just does not have enough math language to say that, to deduce this. So he was crying for a higher mathematics. And what is the higher mathematics mean? And now, 6 decades after, here comes Bernoulli posed this fast descent question again. Well, he didn't just pose it. The gentleman even made it into a challenge. That line is some Austin, 400 some years ago. And he mailed this to, at that time, leading mathematicians in Europe, Leibniz, L'Hopital, and so on, right? And here comes our famous one night, right? Well, bingo, of course, for this gentleman, even 10 years ago, right? This gentleman, 10 years ago, he published his Principal, and not just mentioning a little ball, right? He knows every single thing in this universe. Not just a little ball, from this little ball to the Jupiter, right? From the apple to the neighbor sitting next to you. He knows what happens before, what happens now, what will happen the next moment. The apple doesn't jump because it wants to jump. The planet doesn't turn around the Earth, the sun, because there's an angel pushing it. It's because of these fundamental principles, 3 fundamental principles plus the gravity. Describing a system of mathematical language, he can solve every equation. The solution tells you the past, current, future. And Newton totally changed our point of view of his point of view, right? And here comes he gave the confidence that got lost before back to our hands. We can that comes enlightenment, the age of reason, right? With the reason we can create machines, with formulas we can design futures. And well, at least for a moment, we are very happy. We're very happy, and then to describe, but to describe Newton's law, to design your engine, the new higher math you need nowadays we know is calculus, right? Because this principle, the principle described by mathematical equation involves derivatives. That is new, and then it takes then there's a side emergement of mathematician Lagrange and so on, right? You start from Euler's very intuitive calculus to finally, in the later in 19th century, with the Weierstrass's strict language of epsilon delta, we mathematicians, with our little articles by article, papers by paper, we build the foundation. It's not easy. You explain a real line strictly take you 1 or 2 lectures, right? And you cannot just it's, well, at the beginning of 19th century, actually, mathematicians realized astonishing vagueness in the foundation of calculus. It's not said by me, it's by Abel. Abel found, he was for rigorous foundation, right? And only with this rigorous foundation, we can have confidence to move on. Like Maxwell actually used differential equation and predict some non-existing physical phenomenon in the lab, and later on people recovered it, right? And for physicists, they think there's nothing after Newton until the next excitement of Maxwell 200 years ago. And for mathematicians, we're working hard for this foundation to for the next move on, right? And okay, so back to the fast descent. Well, as this chair of female professor, I would like to draw attention to underrepresented. So there is a student of Bernoulli, Maupertus, Monsieur Maupertus. There's something very concerning for Maupertus, right? So if you have a little ball dropping from A to B, fast descent is not the straight line, right? Then if the universe does not want to minimize distance, then what does the universe want to minimize? Must be something the universe want to minimize, right? And Maupertus think it's a quantity called action. But Maupertus received a lot of mark and criticized even until that. But his idea, his belief in this concept of action inspired the other 2 gentlemen, Euler and Lagrange. Euler put several extra conditions inside Lagrange and changing this summation. They change the summation into integration, and then comes the Lagrange, the entire new way to formalize mechanics and Lagrange mechanics, right? And turns out what? Turns out this concept of action actually has a longer life than Newton's laws. It survives to quantum world. Well, I guess it's because this concept of minimization, the concept of stream, is more fundamental than, the fundamental principle. It's so the observation over here is that, well, you see like maybe my name will be certainly buried into the sands of history after another couple hundred years, like Malpatos. If I didn't try to prepare this lecture, I wouldn't know his existence. And but I want to say that but maybe I can pass some ideas to you, and you pass on to other people, enlighten other people. Well, today we go back to write our articles, submit to famous or non-famous journals. But at the end of the day, if these ideas, some of the idea, like what Malpatos did, or Lagrangian, continued, like surviving in the long, in the science history, and that will make the fire of human culture continue. That's the and okay, so much about and now then the physics sort of turned more from the geometric intuition to a analytical equation solving based problem solving. But we're visual animals. Human beings, we are visual animals. 80% of information of our brain received is visual. We need geometry, right? Then geometry, actually later on, geometry returned. How did the geometry return? Well, it turns out Lagrangian mechanics operates on tangent bundles. And mechanics is on cotangent bundles. In between of them, there is a Legendre transformation connecting them. And bundle, on cotangent bundle, it naturally has symplectic form, which is a closed non-degenerate form dpdq. P is the momentum, Q is the position. And it's not a non-degenerate. It means that it forms an isomorphism from tangent to cotangent. It is a two-form, eat a vector and gives you a covector, right? That's an isomorphism. And that gives you a symplectic manifold. Once you have a symplectic manifold, Arnold further defines a Lagrangian submanifold. Lagrangian submanifold. It is a half-dimensional submanifold such that you restrict omega on L is 0, and a very obvious submanifold for T itself. Alan's observation, Alan Weinstein observation. So here, when you have two manifolds, they talk to each other by a symplectic morphism. So you see, you got your gadget, your object. The next step is to study how they correspond to each other, right? They correspond to each other via morphism, symplectic morphism. But sometimes symplectic morphism is not enough. And here he observed that the graph of a symplectic morphism is a Lagrangian submanifold of the product. Only that you need to turn the first copy with a minus. So you need to put a minus sign on the symplectic form of M. So here you can interpret a symplectic morphism as a Lagrangian submanifold. And here's Alan's slogan that everything is Lagrangian. A good way to organize your system is put them into a category, right? And later on we'll see it can be a homotopy category further. And the objects are these symplectic manifolds. And morphism now, as we observe, it should be Lagrangian submanifold from the first copy with a negative symplectic form product with the second copy, and so on. And now you can compose them. You compose them by intersect two Lagrangian submanifold. You pass the information of the first Lagrangian submanifold to the middle manifold and transfer it to the second Lagrangian submanifold. This provides you a composition, but with the precondition, these two Lagrangian submanifolds need to be transversal to each other. And therefore, we put category in quotation mark. What if it's not transversal, right? Then you can compose. That's not good for a category. You need to compose any maps you want, right? And here comes more like a zoo of Poisson geometry. A lot of colorful geometric object that people discovered, inspired from dynamic system, and so on. Here you have Poisson manifold, derived manifold, Poisson Dirac Courant, algebraic Courant, and the generalized complex structure and generalized scalar structure of our friend Marco, and you see it's like a tourist come to Barcelona. Beautiful, colorful Casa Mila, Casa Batlló, Sagrada Familia. They are beautiful, colorful, full of imaginations. Pa. I feel there's a architecture behind it, right? So when you see all these colorful animals in this zoo of Poisson geometry, you feel there is an architecture behind it. What are their nature, right? So here we've got all this curiosity, and here is a limiting situation like Galileo and Newton are facing, right? And before answering them, I want to mention another curiosity over here. So here's Emmy Noether, and she's got this profound insight, like in a physics system. Whenever you have a symmetry, then it give you a conserved quantity, and whenever you have a conserved quantity, it corresponds to a symmetry. And I'm pretty sure that if this female excellency professor was able to be established 100 years before, Emmy probably will be here too, right? And she probably will observe symmetry in Spain and wonder what are the conserved quantity behind it. And whenever I get depressed, I go to past her apartment. You see, she stays. This is the apartment she stayed until she left Germany because of Nazi to U.S. It's a very modest apartment, and she never had a tenured professorship in Göttingen, even before leaving, and well, compared to what Gauss had. I don't want to be bitter. The whole Villar. And but still, like this profound her profound insight stays, and mathematically, you've got a symmetry, namely a vector field generated by the algebra on your manifold. Like you have a sphere. The symmetry is this rotating, so vector field is horizontal along the latitude. And then there exists a moment map that's the quantity part, goes from manifold to the dual of the Lie algebra. So when you do this rotating of Earth, the moment map is the projection on the height, and then they correspond to each other through this equation. Well, because omega is non-degenerate, so it's 1-to-1 correspond. Omega eta vector gives you a covector, and this map is isomorphism, so it's 1-to-1. And then once you have this, you can that leads to Alan Weinstein's symplectic reduction. You can take, for example, a level set of 0 and reduce by the symmetry, and that gives another symplectic, smaller symplectic gadget. If you believe symplectic geometry is the geometric framework of Hamiltonian system, you get the reduced phase space. And then what if 0 is not a regular value, right? And what if the action of G is not free and proper? Then if 0 is not a regular value, then you are facing the problem that this gadget is not a smooth manifold. And even if it's a regular value, if your G action is not free and proper, then the reduced quotient space, we know that we have singularities, right? And how are we going to facing these limiting situation? Like we're at the edge of like a rigorous foundation now, like what calculus has faced, to directly facing to explain limit, right? And here comes this Grothendieck, and he provided a higher. He introduced this higher derived framework in algebraic geometry to treat such problem universally, to provide a universal solution for this. And then Jacob Lurie and Toan Vizzozzi they advanced this idea by going to higher categories and higher derived algebraic stacks. So these are the two foundational work of Toan Vizzozzi, and this thing is amazing. Like this website, Lurie had his 3,000 pages of continuous, connected logic. Like I won't be able to do them, about 100 or at most 150 pages of continuous logic is my limit. and and then all of a sudden your space is bigger, like you have high degrees and derived degrees and provide you a lot of space. These space provide over here give you can do at least two things, right? One is to help you to resolve singularity in the limiting situation. It turns out there are two sort of limiting situation: limit and co-limit. And also your symplectic structure, like in symplectic geometry, you have space to get shifted. Now, why do you want to shift? The physics nature is that our universe is not one-dimensional. Our universe is 3 plus one-dimensional. And so if you look into the standard model, in the sigma model, the worst is of a higher dimensional. That suggests you, the worksheet is the source of the sigma model, right? Then it suggests you the target of it is not just BG, right? It's it's not just the nerve of a group, like Digraph-Wheaton model. It should be nerve of a higher group, so you should have higher structures pumping out on the target. And if you believe TQFT is a functor, then TQFT should be a higher functor. Therefore, the higher and derived language, well, from my point of view, I think it provides a mathematical language to make the modern physics with a greater clarity. And well, there's a lot of reason and to study this, right? So let's go back a bit more concretely. How are we going to use this higher and derived language in differential geometry and solve all the puzzle limiting situation that I pointed out before? So as I told you, there are two singularities, right? So this is the first sort of singularity coming from like a co-limiting type of singularity. For in plain language, is some sort of quotient singularity that is co-limits. So when you have a Lie group axial manifold, if the action is not free and proper, the quotient is not a smooth manifold anymore. For example, you rotate your R2 with S1, then you've got the quotient as a quant, right? And is a quant, and here at the zero you got a singularity, and then you have a very easy to resolve this. You resolve with action group, right? If there's something. So this it's such a pair that the things inside is such a pair, and you should remember it, imagine it as a arrow go from X to GX, and if you have such pairs, two such arrow, the source and target need to match, and the composition is simply you multiply these two. So that's your action group, right? First is the source of this thing is X. That's the source. Target of this X. So you see, like once you get into action group, right? Everything is smooth. This guy is a smooth manifold. This guy is a smooth manifold. Source and target projections or multiplication actions, they are smooth maps. Multiplication is also a smooth map. So even though your quotient might not be smooth, right? But your action group right is a very good replacement. And turns out whatever you want to do over here, like a theorem, complex, whatever, you can do it instead of over here. It gives you an equivalent answer. So that resolves your quotient singularity uniformly. And of course, once you accept groupoid, you can never stop over here, right? You'll have limiting situations like or what the level 1 also have some quotient singularity. You need to repeat the resolution. And then in the end, you will get one of those infinity groupoids, which is a simplicial manifold with certain combinatorial condition called Kahn conditions. This generalizes the concept of groupoids. And a simplicial manifold you think has, well, I think people are familiar with simplicial set, which comes from the simplicial decomposition of a topological space, right? X0 is the set, could be think as a set of zero simplices. X1 could be thought as the set of one simplices, and so on. And here is just that in addition, there's a set, you also have manifold structure on it. We'll talk about these things in July when I come back for a longer term of a visit. Probably a form of mini course, and Kahn condition. Oh, that's really nice combinatorial condition. Kahn condition says that for example, over here, that's Kahn 2, 1. It says that from X2 to the Horn space, it's a surjective submersion. Horn space is like two edges glued together at this point. And what does that say? It says whenever you have such a horn, you can fill it with a triangle. Therefore, the third edge can be viewed as a sort of multiplication, right? A groupoid you need to multiply. Sort of as a sort of multiplication, and since this is it's not just the isomorphism, it's surjective submersion, you might have multiple multiplications because you have multiple ways to fill the horn. But different multiplication will differ by a homotopy that's dictated by higher Kahn condition. And the homotopy might not be unique, but two different homotopy will be differed by another homotopy that's dictated by even higher Kahn condition, and so on and so forth. That's how you imagine an infinity groupoid. Multiplication is not unique, but unique up to homotopy. That's how you imagine these. If you don't like this Kahn condition, well, Florian Dorsch, he provides you a way to skip it, because near the identity is automatic. It satisfies automatic locally for these symplectic manifold. That's very wrong message. Set word of manifold, it's okay. And so therefore you could, if you just care about the tangent, you can forget about Kahn condition. Even simplicial manifold can give you a tangent, and that turns out to be non-positively graded complex of vector bundles, and it even have an NQ manifold structure, or if you want, it's L infinity algebraic. And I will provide this is more details in summa about these things. So this is one the differential geometry language to understand colimit type of singularity. And the other type of singularity is a limit type, namely when you have a non-regular value, when you pull it back, it is singular, but you can also resolve it with a very simple model, which is just a quasi-smooth manifold. Quasi-smooth manifold is a vector bundle over M with a section coming back. Simply like this. Therefore, for this moment map, if it is not, if 0 is not a regular value, instead of remember mu inverse 0, you remember this vector bundle, even trivial, right? Trivial vector bundle with a section, namely provided by this moment map, mu going back. Simply like this. Mu inverse 0 got replaced by this model. Well, it can provide this because there's a whole machinery behind it, right? Not G equivalent. You don't need it to be G equivalent. It's when I try to understand mu inverse 0, I do not have the information of G action, right? Oh yes. So this is just an example. Like it happened to be the Hamiltonian system, but if you have any function, mu goes to from m to n, you can understand in this way. And then you have the whole system framework to support this, right? So you actually have the framework of DG manifold, and that's a very good model for differential geometers to use this derived concept. Derived, it's a very good model for derived manifolds. And it's, you see, you don't just have one vector bundle, you have a bunch of vector bundles and a bunch of lambdas. Lambda 0 is this mu, is a section. And lambda 1 is something going between these guys, raising the degree. So it looks like a differential. Lambda 2 looks like a bracket. And they satisfy higher Jacobi identities. So for people who know L infinity algebras, this is the section form L infinity algebra, curved L infinity algebra. And I can go more on this topic of derived manifold in summa. And then when you equip it with these two tools to understand the limiting situation, you combine them, right? One helps you to understand a limit type of singularity. The other help you to understand colimit type of singularity. You put them together, then DG infinity group wise, which is a DG simplicial manifold. Simplicial DG manifold satisfied also its Kant condition. Now each X is a curly one, is a DG manifold. That will help you to resolve all type of singularity. And they have and this gadget has framework to support it. So you put them together. For example, you put DG manifold together. It's a homotopy category. A way to describe this homotopy category is by this category of fiber object. by Baron Liao Shi, which I call you can call it civil, and you put these Lie groupoids together, namely groupoids in the word of manifold together, it's almost there. It's only a ICFO, incomplete CFO. And then you combine these two things together, you also have a ICFO. And this ICFO and CFO is some sort of homotopy category that will give rise to an infinity category. So the axiom help you to put homotopy data inside a category. And there are also other works of Behan Getzler. They work on analytic infinity groupoids, and Kachidi, Reutenberg. They have DG infinity schemes instead of DG manifold. And then the tangent of this DG infinity groupoid, this DG infinity group, they become entirely a Z-graded, not just positive, non-negatively Z-graded. It's entirely Z-graded vector bundles. And once you have this, come back to the symplectic form, right? Symplectic form is isomorphism between tangent and cotangent. Now your tangent is just on degree 0. It got like the entire row, right? So it's a Z-graded tangent complex, and then you have a Z-graded cotangent complex. Then you have room to shift. And now you can allow shift, and then an M-shifted symplectic form is a quasi-iso between this tangent and cotangent shift by M. And quasi-iso means that it's not exactly isomorphism of chain complex, but the homology is isomorphism. Now we have enough tools. Let's come back to our puzzles. How are we going to solve this composition, right? This symplectic category. How are we going to? So this turns out to be harder, and the nature is a bit it is solved quicker. So these Poisson and derived manifold turns out that they are one shifted symplectic, and Courant two shifted, and generalized complex that holomorphic one shifted symplectic, and this and then to solve this thing, it actually combines with the next problem of this symplectic reduction. Well, remember Alan said like everything is Lagrangian, right? So like a long time, in the 70s, he already observed that Hamiltonian G action, they form a Lagrangian in T star G. And further on, Kalag and Safanov, they can further interpret reduction as a Lagrangian intersection. One Lagrangian is here. So the theta is a group. It turns out to be the cotangent of BG. BG is this guy. Or BG sitting inside cotangent, as we said, the base manifold sitting inside the cotangent is the Lagrangian. And the other Lagrangian was done. They if you have two Lagrangian M-shifted symplectic manifold, second, since the thing is one shifted, and the intersection will have to be a zero symplectic object. Therefore, the symplectic reduction, exactly the reduction. But it, and you got 2 Lagrangian, you get 0 shift. From this, you need homotopy pullback. Fiber replacement, you cannot get an easy model, but to get an explicit model, we can work observation. It's replacement of the function is diagram direction. Tangent solve this thing. It turns out here the sum platform is the sum platform on M. Here the sum platform is this guy is T star G. T star times G is the cotangent bundle of G. So you get the canonical form. This guy gives you the quasi-iso. Therefore, that A 0 shift. And so in summary, and the symplectic reduction can be modeled by this DG group, right? For me, well, believe me, this is already very short. This is a explicit. The other solution is really long, and using the homotopy theory of what I pointed out, this ICF and CF, that one is really long, and then the punchline is that this very simple DG group, right, with 0 shift symplectic structure actually gives you this homotopy pullback. And I hope I can tell you more in summer when I come back. Uh-huh. Oh yeah. So you see thank you, Marta. And you see talking still like like this concept of action survives in quantum world, and there's a task for Poisson geometry, namely always want to quantize our system, right? But we're still now staying on the classical mechanics level, even though we are resolving the singularities. We can shift symplectic forms, but then we also want to, in the end, quantize these shift symplectic form, and to do the quantization explicitly, right? You, like what I do here to treat the reduction explicitly. You need a explicit model of, for example, 2 Hilbert space, right? So when you do quantization, you need Hilbert space and some system algebra or von Neumann algebra, and over here to perform this explicitly, you need at least some explicit model for 2 vector spaces, and they are there are there are proposals for these two vector spaces, right? Like a base, all they have this chain complex of vector spaces. That's very simple, but it's not enough. And for example, the K theory built on these on two vector spaces. They are not higher K theory, namely TMF. There are some two copies of K theory. So that's a hint. It's not enough. You need to find more complicated two vector spaces. Another proposal is from Stokes-Teichner's program, right? They use phenomenon algebra and bimodules and intertwiner of bimodules. That's a two category, and that's more analytical approach to these two vector spaces. Konrad Vardov, they are building more such true representations. Enough, it might not. I don't know, but there is more like a more soft version, like a less analytical version. That people like how should students working on it, and Chris Douglas, Andre Henriquez, these people, they're working on their K-linear categories. And maybe one needs to wait a bit for the development of, but maybe one, yeah. So I think that if I choose, I will choose these two vector space to work on for representations. Thanks.